do a literature search, and I think you name any material and you will able to find out it is being deposited in the form of thin film by the pulse laser deposition, which may be difficult by many other technique. And not only that it can be deposited, it can be deposited with a very fine precision. So this is the schematic of the pulse laser ablation. Since as I already mentioned that we do require the vacuum and the low pressure gas, so we have to have a sort of a chamber which has the capability in which is equipped with the evacuation system and the pressurizing it with the low pressure gas, and therefore one requires a multi-port chamber. So this is a multi-port chamber here. And since the laser has to be inserted onto the target, so it should have a viewport. Of course, the advantage with this system is that the lens can be kept outside. So apart from the target and the substrate, everything can be kept outside. So the contamination onto the various component is, particularly the delicate component, is not the concern at all in this case. So the laser can be inserted through one of this port onto the target, and the target is inserted through this port. I will show its photograph shortly. And the opposite to the target, the substrate is inserted, and this is equipped with the heating arrangement. Then we have to monitor the pressure. So there are the few ports to monitor the pressure. Sometimes the plasma is to be monitored, and of course we do measure the plasma parameter. That is another the research area of interest, or which is interest to me. So we do a lot of work onto the characterization of this plasma. So some ports are there for that. And then since the low pressure or the reactive gas is to be inserted, so we have the gas inlet port. Then this is a gate valve for the isolation of the vacuum chamber, and below that it is the turbo pump, which is backed by the rotary pump. So this is the highly schematic diagram of it. And here is the photograph of this one of the chamber which we have in our lab. So this is the multi-port chamber, one can see. And this if you see, this is the focusing lens here. This is the laser. Laser is being steered with the help of a 90-degree prism, and then it enters here, and this portion is outside the vacuum. And here is the lens. One can see, since we are using the second harmonic of Nd:YAG laser, so which is at 532 nanometer, one can see the green spot here, and this is the port through which it is entering. And this is the substrate holder, and this is the target holder. And then there are the various viewports to observe the plasma, to monitor it. So whenever we have to monitor the plasma, we put the diagnostic across these ports. And then one can see there are some gauges are mounted here. This is the one gauge here. This is the one gauge here. And there are one or two more gauges onto the back side of it, which is not visible. Here is the gas inlet line, and one can see this blue wire kind of a thing. This is the gas line. And then this is then this is the gate valve, and below this table is the pump. So the pump is just below this, and then we have the various controllers. So this is the control for controlling the target stage, and then some of the gauges are mounted onto this panel itself. This is the flow meter. This is the heater, monitoring the heater and controlling the heater temperature, cooling rate, rate of heating, etc. And then the few panels are below this which are not visible. They are the gauges for monitoring the vacuum, etc. Now, if we try to view through this viewport, from the top viewport, so we peep through the viewport, what we see is this kind of a thing. So this is a target carousel on which the target can be mounted, and this can mount the 6th target. And since it is going to mount the 6th target, and the laser will be focused only one of the targets, so it has a provision, and the laser is fixed. The focusing point for the laser is fixed, so this can be rotated. I will show you in the next slide. And this is the substrate holder stage. Substrate is holded by means of these clips. One can see these clips, and then this is the heater to control the temperature of the substrate. This is the carousel stage, which can hold the 6 targets. So the 4 targets are mounted here, and these 2 targets are empty. So here I think where it is. Yes. Any question? Hello, any question? Okay, I think somebody has unmuted his mouth. Okay, fine. May I request the participants to mute their microphones? If you have a question, please ask. And this, so in order to change the target, these targets are mounted onto this big disk. So this disk can be rotated like this or this. And when we focus the laser at one point, what will happen with the repeated impinging of the laser radiation, material will ablate. So these targets are rotated about their own axis. So these targets are rastered about their own axis, and whole of this plate is rotated about its own axis so that the required target can be brought for the deposition. So this is the, in a very brief, about the pulse laser deposition system. Now there are the several challenges also, though the technique is in principle very simple, but there are the challenges. Particularly the challenges which we faced was the deposition of the pure metal film. The pure metal means that it is a deposition of copper, silver, rhodium, etc. So the problem with these material is that they are highly reflective. So the reflectivity is around 90% or so. So the hardly 10% of the radiation will be absorbed by the substrate, and then the plasma will be formed. Another problem is, since the melting point is not very high, and since they are a good conductor, so the material partially the material comes out in the form of the liquid droplets, and those liquid droplets, they may get deposited onto the substrate, giving a very poor quality of the film. And then, of course, the oxidation, particularly once we are dealing with the copper and the molybdenum, etc., they are prone to the oxidation. So the vacuum quality has to be extremely good. So these are the three challenges which we face, but with the proper optimization, carefulness, one can overcome all these challenges. Here I am just trying to demonstrate the example of the rhodium film. Here RH1, RH2, RH3, they are the rhodium sample. It reminds me that the last year I was giving a talk and I was sharing this slide. So some of the speaker thought that I am talking about the various isotopes of rhodium. So rhodium 1 something, rhodium 2, rhodium 3. So just let me clarify that these are not the isotopes. These are the various samples which are deposited at the different target substrate distance. So here I just demonstrate the thickness as a function of the target substrate distance. So when the target substrate distance was 3 centimeter, we got the maximum thickness of 90 nanometer. Of course, this was for the deposition time of 1 hour or something like that. And then as the distance was increased, the thickness started decreasing. And the reason is, since this is in the vacuum and plasma is freely expanding, so as the distance is increased, the target substrate distance is increased, plasma is expanding, so the plasma density is reduced, and therefore the deposition got reduced and the thickness has fallen down. So now, in order to control the thickness, what we did was that we tried to confine the plasma in presence of helium gas. Helium is a neutral gas, so it is not going to do any chemical reaction with any of these compounds and any of this material, or any of the material per se. Even if the helium is getting ionized, it is not going to do anything. So we have seen that when we do it under vacuum, we have the 120 nanometer thickness. And when we try to increase the pressure around 0.5 millibar, we got the thickness around 270 nanometer. With the further increase, the thickness has fallen down. The reason is that when it is freely expanding, obviously the density of the plasma is falling down, and therefore the thickness is less. When we slightly confine it, then the density has increased, and so the deposition has increased and we get the higher thickness. But when we cross certain optimum, so what is happening is that the plasma is over confined, and the size of the plasma is becoming smaller compared to the target substrate distance, and hence the distance is falling down. So the take home message is that whatever film we try to deposit, we have to do the optimization. Either we use the ready-made recipe which is already shown by others, but then we have to keep all the parameters same. But if we try to change any of the parameter, even if we try to change the intensity, we again have to optimize all these parameters, and then we will able to get the desired quality. The another limitation which is viewed particularly till 90s or the 2000 was that the pulse laser deposition technique is limited to a very small size. Maybe one can deposit hardly the 1 centimeter size or the 1 centimeter diameter. So we try to overcome that thing by having the connecting the substrate with the motorized stage in the 2 dimensions. So what we did was that we have the two motorized stage coupled together. One is along the x-axis and the another is by rotation. So in this way, we were able to cover the large area of deposition. And here I will like to demonstrate again the some optimization is required. Of course, the speed of both these speeds, the RPM as well as the linear speed has to be optimized. And then the location of the target and the substrate also has to be optimized. So as an example, I am trying to demonstrate here the three locations. In one case, here is the target and here is the substrate, and the target and substrate, their centers are facing to each other. So they are concentric in a way. And then if we try to rotate the substrate, what will happen? The deposition will be, and the plasma size is this much, whereas the substrate is bigger than the plasma size. So what will happen? In the center, the above photograph is that of the film deposited. In the center only there will be the large deposition, but the surrounding area, the deposition will be less. So if we make it off axis, in this case, the second case, it is two off axis. So in this case, what has happened that in the center there was hardly any deposition. One can see that the sort of a donut kind of a deposition has taken place, and with the careful, if we enlarge it, one can read the whatever is printed in the center of it. So that is why deliberately these samples were kept onto the printed paper. And the substrate used was the glass. Of course, there is no restriction with the substrate, but here we have used purposefully the glass substrate. So this the location has to be optimized, and then we optimize the location. We brought this the slightly more closer to the center of the target, and then we could see the uniform deposition. It was completely reflecting and completely opaque. So, and the uniform deposition. So this is the when we are depositing the large area films, we have to do the optimization again and again, depending upon what is the size of the film we want to deposit. In the recent past, I have seen that some of the sensors application, series of the sensor application, it was demonstrated up to the 20 centimeter. We have demonstrated up to the 2 centimeter, and then beyond that, since this was the project under the National Fusion Program. Of course, now that is merged with the BRNS. So there the requirement was of the 2 centimeter of these thin films to be used as a mirror into the tokamak plasma. So we have done for them, and we have given this sort of a mirror. Now, since it was deposited for the mirror, so the quality has to be very good. And this slide demonstrates the quality of the mirror. These are the 2-inch diameter mirror. And this was and these were deposited onto the SS, because in the tokamak only SS was allowed, the glass was not allowed. So this was the substrate without deposition, and this is the one which was deposited one. So this is the simple interferometer. The interference pattern was recorded with a simple Michelson interferometer, which is now we find it in every college demonstrating for the graduate program. So one of the mirror of the interferometer was replaced by these mirrors, and one can see the parallel fringes. So the perfect parallel fringes is the clear-cut demonstration of the quality of the surface of the film, because the reflectivity also gets affected if the surface quality is very poor. So here the perfect fringes clearly demonstrate that the quality was very good. The one parameter which measures the quality of the film is the fringe visibility. So when we use the commercial mirror in the interferometer, both the commercial mirror, the fringe visibility was 0.84. When we replace one of the mirror with this our in-house fabricated mirror, it was 0.8. So this was a very good quality. So many times people go with the perception here, pulse laser deposition, probably the quality may not have the control, but here we have demonstrated the quality over, we have demonstrated over the 2-inch, but later on I have seen relatively recently that people have deposited it even up to the 20 centimeter size and very good quality films. The another example is the tuning of the band gap, the thin film with the tunable band gap. Here I am trying to show the example of the Jadeno film with the aluminum impurity infused into it. And the idea behind that was to increase the band gap of Jadeno to go into the more and more ultraviolet direction. So here one can see this, the blue dot indicates the band gap of the AZO, aluminum infused ZNO. I don't want to use the word doping. People use the word doping, but the doping is the extremely small quantity. But here, this is not an extremely small quantity. It is of the order of, one can see the percentage composition is 0.02 of aluminum. So this is not the doping, I will just say the infusing. And one could see that with the increase in the aluminum concentration into ZNO, the band gap has increased. But after attaining some optimum value, it has fallen down because with the large quantity of aluminum, it was becoming conducting, and that is why the band gap has fallen down. Now the question comes that where do we find application, particularly in connection with photonics? So here I would like to demonstrate it, that where this kind of the film we have used into the photonic thing. So the example here is the random lasing. Laser, as we know now, of course, it has gone to the classroom level, and we demonstrated that we have in the laser active medium, which is pumped so that it is excited. Of course, the active medium has to be selected carefully, which has a capability to give the laser action. And then the two mirrors are placed. And if the situation is set properly, the radiation will emit, stimulated emission will grow, and then through one of the mirror, it will come out. So this is a well-defined cavity. But in case of a random laser, we are not having a well-defined cavity. So here the particles are there, and they are randomly oriented, just like a thin film. And what happens is that through the scattering of the radiation from one particle to another, we get the stimulated emission. So suppose that this particle, of course, to begin with, it is the spontaneous emission. It is this particle is emitting the spontaneous emission. Light will be emitted in all the direction, and the photon going in this direction will stimulate this one. And from here, it will stimulate this one. So in this way, we are not going to get any specific cavity like this, but the cavity formation is sort of a random thing. So this is the random laser. And since these kinds of the well-defined cavities are not required, so there is no requirement of the mirror, etc. It becomes very simple, and it could be very small. So in a way, the advantage with this is that we have the mirrorless cavity. And optical cavity, or if we want to say the cavity is formed by the multiple scattering through the particles from one particle to another particle. And normally for the laser, the gain medium has to be a well defined ordered medium, but in this case we don't need any ordered medium. We can have the powder, we can have the thin film having the full of particles. So, but this random lasing is not a very new phenomenon. In fact, after the advent of laser itself, in 1969, this is the paper which was demonstrating which has explored the possibility of the random laser. But of course, now it is becoming much more in coming up, and its applications are being thought of, particularly some of the applications in the area of the medical sciences as a diagnostic thing, and the photonic sensor. So, and the advantage with this is, since it is of extremely small size, so it can be a very good photonic sensors and the lightweight sensor. Just a little bit more elaboration on the types of random laser. So this kind of a completely random laser I already have described. But suppose that we have the particles which are very well crystalline. For example, in case of a ZNO, it is a hexagonal crystal structure, and we do get the hexagonal facet. So in this case, rather than the completely random cavity, we may have these parallel facets forming as the mirror of the partial reflectivity, and the radiation may be developed in this direction, or it could be developed in this direction, or it could be developed in this direction. So in this case, it is forming a sort of a Fabry-Perot interferometer kind of a thing. So this kind of a cavity is called as the Fabry-Perot interferometer, or we can have the whisper gallery mode, which is coming because of the total internal reflection. So suppose that the radiation started from here, it falls onto this adjacent facet of the hexagonal and gets reflected. And if the angle of incidence happen to be more than the critical angle, so for the ZNO, the refractive index is of the order of 2, and the outside is AL, which has the 1. So if we try to calculate from the Snell's law itself, the critical angle comes out to be 30 degree. So if the angle of incidence happen to be the 30 degree, then the complete radiation will undergo the internal reflection. It will fall onto this facet. It stimulate the molecule to undergo the stimulated emission, and then it will fall onto, and so on and so forth. So in this way, it will form a slightly a more organized cavity, which is called as the whisper gallery mode. So we can, but this is again a random because the large number of cavity will be formed. Suppose that instead of this, if it is falling here, then we will have here, we will have here, and so on and so forth. But here the confinement of the photon will be taking better than this, and in this case, this is better than this. So obviously the quality of the laser will be better in these cases compared to this case. So we have our AZNO film, and we demonstrated the lasing action into it. We use, since the ZNO, as you know, the band gap falls around 360 nanometer or 380 nanometer, and it's the emission is around 390 nanometer, 380 to 390 nanometer. So we use the excitation source as at lambda equal to 355 nanometer. So that is the third harmonic of NDR laser. Since we have the very high power laser, and the whole laser, if we allow to fall onto this ZNO sample, its plasma will be formed. So we have to curtail the intensity like anything. So we just use the glass plate so that around the 10% reflection will fall onto it, and that also we have curtailed with the help of the neutral density filter, and then the radiation was focused onto the sample, and then through this optical fiber system, it was fed onto the monochromator and then recorded, and it was fed onto the computer for the recording the data. So the experimental setup is not very difficult. Of course, some alignment is required, particularly on the focusing of the radiation onto the sample, and also the collection optics. So the question is that how do we distinguish whether we are getting the laser action or we are getting the spontaneous emission? So here is the curve which tells us that if suddenly beyond a certain level, there is a suddenly very large increase into the radiation output, that shows that the laser action is taking place. So here at this point, this is probably the threshold. Here I have demonstrated the pump intensity as a function of the laser output. So at this point, this is the threshold, and beyond that, there is a sudden growth of the radiation. Another check is in terms of the mode structure. So laser, we know that there are the periodic modes, particularly for the longitudinal modes, which are reasonably equispaced. So here we got the spectrum of the laser, and we have this periodic mode, and the separation between the periodic mode was around 3 nanometer. And then we just enlarge one of the particular mode to find out what is going to be the FWHM. So the FWHM of this longitudinal mode was around 0.56 nanometer, which is quite narrow. And again, that kind of shows that this is a laser action coming out, and then this is a random laser. Another application on ZNO itself was that after the little bit tuning the conditions, we were able to grow the ZNO nanorods. And then this we demonstrated as the frequency up conversion. So what we did was the previous experimental setup which I was describing here. So instead of using the third harmonic of NDR laser, we use its fundamental only. The fundamental is 1.06 micron or 1064 nanometer, and we excited these rods. and we were via the multiphoton absorption induced emission, we were able to get the band edge emission. So in this way, so if we do not have the direct excitation source, we can use the multiphoton absorption induced emission. And this was also analyzed. I'm not displaying the result of it. And we could see that here also we were able to get the laser action and the longitudinal mode similar to what we have got it with the 355 nanometer. So this can be used as the frequency up conversion easily, as we know that the lower wavelengths are easily available, like 1.06 micron and the few more, but the shorter wavelength radiation sources are not there, particularly the coherent radiation. So the frequency up conversion can be easily used to generate the UV radiation, particularly as a laser and the coherent generation. The second photonic application was we have demonstrated in terms of the thin films of the ruby. Again, the ruby was deposited by a pulse laser deposition thing. The ruby, we know commonly it is a gemstone, and I think at least we see everyone in the 3%, they wear the ruby rings, ruby stone. So this is, we know that it is alumina which is doped with chromium. So we have made the ruby thin film, and one can see its crystal structure. This is the peak showing the woodside face. So very good quality. And ruby, we can recall also that was the first laser into the sort of a visible range, which has the two lines, very closely spaced line, which are called as the R1, R2. So one can see that they are very distinguished. So that itself is confirm or the supplement this result of Raman, that the quality of the crystal is extremely good. Now this we have demonstrated as the photonic temperature sensor. These lines are dependent on they are dependent onto the temperature. How do they depend? The location is dependent onto the temperature and also the separation. It is not a very linear dependence. So here is the variation of the R1 and R2 line as a function of temperature. One can see right from the 100 Kelvin to the 500 Kelvin. I have shown it the variation up to, and one can see the good variation. Earlier we used to always think that the sensor should be linear, but now we know that since we have the very good advanced data analysis technique, so we need not to have the sensor to be linear. We can have the data analysis technique and we can have the calibration curve, so that even if the sensor happen to be non-linear, it doesn't matter. So these can be very well used as this thing. And the advantage with this kinds of photonic temperature sensor is that they are immune to the noisy environment. They are not sensitive, since these are the dielectrics, so they are not sensitive to the magnetic field, they are not sensitive to any RF noise. So one can use them in any of the environment. And the temperature range is also very high, because the melting point for the ruby is extremely high. It is more than 1000 Kelvin probably, if I can recall correctly. And it can go to the very low temperature also. And it is going to be in a very miniature form. So that is another advantage, that it is a very light photonic sensor. The third application of the pulse laser deposited film was the plasmonic film. Here I am trying to demonstrate the plasmonic property of the copper. Thin film, these are the extremely thin film which are the semi-transparent. One can see from here the deposition time and the thickness. So the one can control the thickness with the deposition time. And depending on the deposition time, accordingly the micro nanostructure of the copper thin film varies, and accordingly its plasmonic properties varies. So one can control its plasmonic property very easily. Now I go to the second application of the laser interference lithography. The basic principle, we can say that it is a sort of the selective ablation of the thin film. And using this technique, we can modify the surface morphology, where we can generate the structures of the order of tens of nanometer. So the principle is, let me demonstrate it with the help of this slide. So if we have this kind of an interference pattern, simply the two beam Michelson interferometer, which can be obtained from the Michelson interferometer, and where we have the parallel lines. Now if we try to plot the intensity here, then we get the cos square kind of a curve. So this is the high intensity region, and this is the almost the zero intensity region. Now, if we eliminate the thin film or the surface on which we want to do the writing with this kind of a interference pattern, and suppose that the threshold for the ablation is this solid line. So what will happen? The material which is in this region of the region of intensity, where the intensity is much larger than the threshold, material will get ablated, leaving behind this bottom region unaffected. So in this way, one can have the pattern of the size much less than the lambda by 2. Of the periodicity is going to be limited by lambda by 2, but the structure size will be much less than this lambda by 2. How do we do it? So in a way we are selectively ablating it, so we call it as the selective ablation. And as a result of this, we can write the grating sort of a structure. So experimental setup is very simple. One can have the thin film. Thin film, one can have it from any kind of system, whether it is the pulse laser deposition or any other system. And we have the Michelson interferometer. So we, of course, here the laser has to be high power so that the material can be ablated. So we have the Nd:YAG laser, and the collimation probably normal is not required, because Nd:YAG laser itself is quite a high power laser itself is quite a big beam, 7 to 8 mm size. So normally the collimation and the expansion is not required. And then this is the Michelson interferometer. So this is the beam splitter. So the part of the beam gets splitted and gets reflected, goes to this mirror 1 say, and from here it gets reflected, falls back onto the beam splitter, and again get splitted, and part of beam comes out here. The beam which is getting transmitted directly falls onto the mirror M2, gets reflected, again reflected from the beam splitter and falls. So in this way we have the two beams onto this side, they interfere and gives us the parallel fringes, and one can write it very easily, the grating kind of a structure. And this one can perform either under vacuum or under air. We have performed under both the things. So we have tested this, we have in fact made it onto the variety of thin films. And here is the one of the example I would like to share, that one is able to write all these parallel beams. This is the scale here is the nearly 100 micron. And this was written onto the vacuum evaporated indium thin film. So here the size is quite large. So what we have done was that we have slightly compressed the interference pattern and loosely focused it onto the thin film. If we tightly focus it, then we will get the two spot. But we have to have the overlapping region of the two beams. So we have loosely focused it onto this. And this is how we could compress it. And this, one can see that within a length of the 20 micron, we have the I think this is slightly more than the 20 fringes. So the line thickness was less than 1 micron here. So in this way, one can write the fine structure. And this is just the parallel line. So the one-dimensional writing. One can even do the two-dimensional writing also. So for the two-dimensional writing, what we have done, we use the two interferometer in tandem. So this is the Nd:YAG laser beam was steered suitably, and these two mirrors. And then this prism, they form the one interferometer. So the two beams are coming out. So this interferometer, for example, we set it so that we get the horizontal fringes. And then these two beams enter into this another interferometer. And with this interferometer, we make it vertical. So what we get is the interference pattern in the form of the square array. And now this square array is allowed to illuminate the vacuum, illuminate the film. Either it could be in vacuum or into the air, but we wanted it to be to write it of the order of the wavelength, the periodicity of the order of wavelength. So we don't want the evaporated material or the ablated material to get redeposited. So we did it under vacuum. So this is the interference pattern which we recorded, and then we illuminated it, and we could get the this kind of a matrix. This is in the scale of 20 micron by 20 micron. Again, further it was loosely focused to get the periodicity touching of the order of 593 nanometer, and this was done with the 532 nanometer. So we are almost touching the limit. And here the width of the writing. So these are the bright spots which shows the unaffected material. So this halox, this shows the material intact, and the valley is in this. This is the 3D AFM images, and the valley indicate the ablated region. So this width was around 263 nanometers, so which was almost half of the wavelength. So this is how the two-dimensional writing can be performed. What are the advantage of this technique? First thing is that, as I told you, the pulse laser ablation in general is a very general technique. So it is applicable to any material. The complete writing can be done in a single shot, single step. And the structure size are tens of nanometer. Setups are very simple. In fact, these are the techniques which are even used by the Intel also for making their some of the chips. Of course, there everything is they're classified, so we do not come to know. But one or two of our students happen to work into this area, who has worked with me and learned the lithographic technique, and because of that, they were taken by Intel. So we, on a casual discussion, those students were telling me that they are using this to make the some of the chips with a high precision. The third application is the laser micro machining. Again, the setup is very simple. The beam is coming from here. It is steered by another beam, is another mirror, and then it is focused with the help of a lens onto the target on which we want to do the micro machining to make this. We have made it from the microfluidic application. This is shown onto the SS, where one can see the channel is very clean and the aspect ratio is also very high. But this is, I'm demonstrating it here onto the SS, but we have done onto the several acrylic material, including the PC, and even we have written it onto the glass also. But the glass, then we have to dip it into the water, otherwise with the shock waves, it will get damaged. So this, the applications point of view, we are still on the way to test that how it is useful into the microfluidic applications. Now I come to the third scheme, that is the laser breakdown into the liquid. So again, the conceptually the setup is very simple. We have the laser which is focused into the liquid, and of course the focal intensity has to be of the order of 10% watt per centimeter square, or the at least the above the threshold of the breakdown of the water. So this results into the ionization of the material and the vaporization and the plasma formation. We can also have it target placed into this the liquid in the bottom. So this photograph is slightly poor quality. So the target is in the bottom, and then the laser is focused from the top. So here is the photograph of the plasma here. So when the laser is focused, there is the target material comes out in the form of plasma, and the liquid is also breaking down in the form of plasma. So this the complete elongated line is the formation of the plasma. This is the entire process of the laser induced breakdown at target liquid interface. This is still a question that how the first atom is coming out, or how the first electron is coming out. But once maybe one can think it over, since we are applying such a high electric field, which I already shown into the beginning of my slides, that the electric field is extremely large. So because of that, all the bonds are breaking, and the electrons as well as atoms and ions are coming out. And then and this process is extremely fast, of the order of picosecond or so. And laser which we are using is of the order of nanoseconds. So these the charged particles, the electrons and the ions, particularly the electrons, they undergo the inverse Bremsstrahlung process to get accelerated, and then they collide with the surrounding particle, and further ionization takes place. So the cascade ionization takes place as a result of the plasma, resulting into the plasma formation and the shock wave. Then the chemical reaction occurs, and the nucleation of the particles takes place, and then finally we get the nanoparticle formation. So this is the scheme which we have applied to generate the, or I can say that the synthesize the nanoparticles. So this is the pictorial demonstration of the same part chart here, that we have the laser is falling onto the target, plasma is being formed, followed by the formation of the shock waves and the formation of the nanoparticles, agglomeration of the nanoparticle, and finally we get the stabilized nanoparticles. We can have again here the three schemes. We can make the noble metal, if we use the noble metal target, we will get the noble metal in the sense that the silver or the non-reactive material, silver or gold. So we get the silver gold nanoparticle, and of course the copper also, but the copper gets partially oxidized also. We may have the system where the pure the material interacts with the surrounding liquid also, and which results into the formation of the composite material. And we can also have the insufficiently oxide material like TiOX, COOX, MOX, which is normally not possible under the normal condition. And these have some of their applications because they are highly active. And these are the metastable states also. So they are highly active. So one can generate these kinds of things also. And application, again, the application part, the list is very huge. Large number of medical applications, dissection, laser-assisted tissue cutting, removal of thrombus in the obstacle arteries, the eye surgery I already told in the beginning. Then material processing also, I have told that the large amount of the material processing. Lithography I have already talked about. Then another application is the laser-induced breakdown spectroscopy, which is used for the detection of the trace element into the water or into any other material. It is also used to analyze the sediments, rocks, etc. Then also it can be used online monitoring of the corrosion in the not only into the nuclear power plants but into all the other hazardous environment, because this is a sort of a non-contact technique. So one can implement it into all the hazardous environment, whether it is the nuclear power plant or it is the high temperature system or it is a very noisy RF system. And then the synthesis of the nanoparticles. And where these nanoparticles finds their application, of course, the surface plasmon resonance is their application. Then another application is SERS, that is the surface enhanced Raman scattering, which I will have the 1 or 2 slides to demonstrate. It is also used for the photocatalyst, and then it is also used as a large number of sensors. Of course, the SERS itself is a sort of a sensor. Because it makes the recording of the Raman spectrum with the ease. So what is the advantage of synthesis of nanoparticle? Because you are hearing the large number of techniques for the nanoparticle. So in this case, particularly the pulse laser ablation or the laser target liquid interaction as a technique for the synthesis of nanoparticle, one thing is it is a single step. Just you have the right kind of the material, right kind of the liquid, and one will able to get the nanoparticle. And it is free from contamination. If the liquid is used which is non-interacting and we need the without the contamination, we can get it. There is a precise control over to the size and the morphology of the particle, and also the crystalline structure and the phase of the particle can be controlled simply by controlling some of the parameters. By and large, there are only the 3 parameters to control. One is the laser power, exposure time for the laser, and the surrounding liquid. Of course, the material, the solid material, which we have to select it depending on to the requirement. So here I just will like to share the results of some of my students. This is the titanium oxide, formation of the titanium oxide particles. And under the different conditions, we get the different kind of the titanium oxide, its phases as well as its the oxygen content. So under the certain condition, we get highly insufficiently oxide titanium oxide nanoparticles. So this was the TiO 1.5 here. Here is the TiO2, but it is the anatase phase. And under some other condition, we got the TiO2. So here we just have controlled the laser power, and the laser power we controlled by changing the focusing spot onto the target, and we got these 3 different phases. So these are the TM image of the various TiO2 nanoparticle, and here they have the size distribution. This is the synthesis of the copper nanoparticle. So here the target we used was the pure copper, and then it was dipped into or we can say it was immersed into the water. And since the copper is quite active and it interacts with the oxygen, so when we immerse it into the water and focus the laser, water molecules also breaks down to give us the hydrogen and oxygen. And this copper and the copper ions, they interact with that oxygen, so they form the cupric and the cuprous oxide also. So we do get the phases of Cu2O as well as CuO, but these phases can be controlled by controlling the condition along with the pure copper phases, which is the cubic in nature. So here the liquid after the laser exposure is shown. So first one is the pure distilled water. Then we have the target, which was exposed, I think, for 5 minutes or 10 minutes. Then this was for I think 20 minutes, and this was for 30 minutes. And then from here to here, we change the power. So one can see that with the changing condition, the color of the liquid is changing. So and this is changing because the size of the particle is changing and their surface plasma resonance is changing, and that is why we can see the different colors into the liquid. Here is the particle size analysis, and one can see that these are all the TM images for all the 5 conditions, and here we have shown the particle size as a function of the laser energy. So by changing the laser energy, one can control the size of the nanoparticles. And this table lists the various phases being formed under the various conditions. So C1, C2, C3 is the changing time for the fixed laser energy, and C3 to C5, the fixed, sorry, it is other way around. C1, C2, C3 is the changing the time with the fixed laser energy, and C3 to C5 fixed time with time means exposure time of the laser with the increasing energy. And one can see that we are able to get the less oxidation under certain condition and the higher oxidation under the certain other condition. So therefore the properties of the nanoparticles can be very well controlled by controlling the laser parameter and the exposure time. Another example is the silver nanoparticle. Again, we have changed the time, and then we have changed the laser energy. So one can see the laser is exposed to liquid, and here also I think the color is not appearing in this photograph properly, but the color was changing, which is again that since the particle size is changing, and of course the concentration was also a little bit changing. So but with the particle change in the particle size, since the SPR is changing slightly, and therefore the color is changing. So this shows the surface plasma characterization of the nanoparticles, and one can see there is some variation into the surface plasma property. In some cases it is very narrow, in some cases it is very broad. And this is the particle size distribution, and one can see from this summary histogram that the particle size is changing with under the various controls. So with the exposure time also it is changing, and with the increase in the laser energy also it is changing. So what happens is that when we increase the exposure, so the particles which are formed with the previous shot of the laser, they get broken up with the repeated shots of the laser. So therefore the size changes. And with the increase in energy, what happens? The liquid droplets are formed, and with the repeated impingement of the laser, the droplet size keeps on reducing, and we get the smaller laser particle size. So this is the summary list of the SPR, peak, FWHM, and size of the nanoparticle. So in this case, the SPR was not that drastically affected, but one can see that its FWHM is getting affected, and the size is of course getting controlled with the laser condition. So where do we use it? In particular in terms of photonics. So we have demonstrated its application for the surface enhanced Raman spectroscopy. Raman spectroscopy everybody knows, so I will skip this Raman spectroscopic slides. So here this is the slide which depicts the principle of the surface enhanced Raman spectroscopy. Now Raman spectroscopy, as you know, that it is that depends on to the induced dipole moment. So if the induced dipole moment is large, then the Raman signal will be large, otherwise it is very small. And we know that the Raman signals are normally very small. So in the presence of these nanoparticles, what these nanoparticles do, they have the excessive electrons, and so they create a sort of a polarization, and once they create the polarization, there is a generation of the electric field, and because of that the polarizability of the molecule increases, and hence the signal increases. This is the one way. Another way is that these nanoparticles, they get attached to the analyte or the molecule which we want to probe, And since they get attached and they have the large amount of electrons, so the polarizability of the molecule increases and it enhances the signal. I will like to demonstrate it with the help of the one of the compound, which was the Karanjin, and which is a pharmaceutical product. Actually, this plant is available in abundance in our campus. So the colleague from the biotechnology department, she said that she will give me these crystals of Karanjin, which were synthesized within the lab itself using these local plants. But this molecule is known for extremely low Raman signal. It was hardly detectable, but we did my another colleague from the chemistry, he did the DFT calculation and showed that the Raman spectrum is there, but of course the signal was very weak. So what we did was we coated this the crystal with the copper as well as the silver also. So here I am just showing the copper, and we did it with the silver. Silver, in fact, we got the better result. So what we did, we just took this crystal and poured that the suspended solution which I have shown earlier, which was synthesized with the help of the laser focusing onto the copper or the silver target in the liquid. And then we tried to record the Raman. So here one can see that the untreated Raman signal was almost negligible. It is shown with the black line. It's extremely low. The counts were not even the hundreds. But when we treated it with the copper and with the silver, it was even much more. One can see particularly these prominent bands of Karanjin, they shooted up to the 8,000. In fact, with the silver, it was more than 10,000. So one can see that it is acting as a very good probe to detect the molecules which have very intrinsically weak Raman signal or which are in the extremely small quantity. And again, here the optimization is required. So with the particle size, particle concentration, we are showing the optimization. So if the particle concentration is very low, I mean to say the copper nanoparticles or the silver nanoparticle, if that concentration is very low, obviously the signal will be low. But if it becomes extremely high, then what is happening was that the whole crystal was getting coated with these particles. And therefore the laser radiation while recording the Raman is not penetrating inside. And that is why the signal was falling down. So again, the optimization, some sort of the optimization is required in these cases. Another application which was not the photonics area, but that is the antibacterial activity of copper. And of course, the silver also we have done. So what we did was that we took the local silk. We already know that the silk is used for the protecting the wound while it is getting healed up, and because it has some antibacterial property. But these antibacterial properties can be enhanced in presence of this copper nanoparticle. So these are the three kinds of the local silk which are very well known in Assam. One is the Ari silk, which is a slightly rough silk. Another is the Pat silk, which is white in color. And the third one is the Muga, which is a golden in color. So what we did was we made a palette out of these silks. And then we treated them with I think some of the bacteria, that is the gram positive and the gram negative control. So I am showing here the two sets. In this, on the left side, it was not treated with the nanoparticle, and on the right hand side, it was treated with the nanoparticle. So when it was not treated with the nanoparticle, one can see the good growth of the bacteria. But when it was treated, one can see the inhibition around this palette. So this shows that the antibacterial properties are getting enhanced, and so it can be used to protect the wound or wherever we don't want the antibacterial property much better. These are the further results. Let me skip it. Now another application we have demonstrated is in terms of the treatment of the filter paper for the water purification, particularly to remove the bacteria from this. So what was done is that the filter paper was taken, the colloidal solution containing the silver nanoparticle, and we have demonstrated both for copper and silver. It was poured onto it, and then it was dried. And then the filtration technique which we have learned right from our school age, it was placed into the funnel by fourfold, and then the contaminated water was allowed to pass through it, and then we have tested the filtered water. and I think the results I have skipped it, but I could see we could see that the when we filter it with this silver nanoparticle treated um, uh, filter paper, we could see that the contamination was at par with the WHO guideline. So probably maybe if I get some funding etc., we may go for the slightly the fabric making of this on the large scale. And since this is going to be very cheap because the silver nanoparticle requires in extremely small quantity, and so it the complete the booklet sort of a thing can be made with this kind of a filter paper, and it can be taken away where the other facilities are not available, the electricity is not available, and the other kind of the filtration or purification technique cannot be used with it can be applied there. I think I'm running short of time, so I want to discuss this calibration free technique. Let me skip it. Uh, so I will just conclude now that I have discussed few of the application of pulse laser ablation and its implication into the photonic technology. Now, before I hand it over to the host, I would like to acknowledge the various funding agency. I think it is not coming properly, but majority of the funding agency is from the government of India, and of course there was a unique concept which evolved I think 3-4 years back by the government of India under the Uchtar Avishkar Yojana, in which we have to have the industrial partner. So this was the scheme in which we had the industrial partner. Then the lots of my collaborators are there. A few of them I have listed from the various other departments. Professor Lata Rangan, who helped me in studying the antibacterial property. Ashwini Sharma is my colleague, and we work together. Um, Dr. Joshi, he is in mechanical, and we have worked on to the laser micromachining with him, and we have completely developed this completely theoretical model to obtain the optimized parameter, and then we have worked experimentally, and there was a reasonable agreement between these two. So that is how the collaboration with the other department helps. Then Professor Barua also is a close colleague of mine, and we are also working with him on to the wavefront sensors, and we had the two patent which I have is in collaboration with him. And then the 2-3 collaborating institute which I have listed is the TIFR, University of Hyderabad, IIT Bombay, and the few more are there. As I told in the beginning, everything is done by the students. And so I would like to thank my students tolerating me throughout their journey for the PhD. And of course, I didn't list my MSc and the BTech students who did their project, and particularly tolerating me, my tough behavior, and um, uh, doing work with me as a collaborator. So these are some of the students who have already graduated, and the few new students I have to yet to update my list. And then there is the very long list of my MSc and the BTech project student who also have contributed at least in one form or the other form. But yes, nothing goes without the student. As a faculty member, nothing goes without the student. So I would like to thank them. And still some of the students are still continuing the collaboration with me. Of course, it is a different field, different than the field in which they did. And we are continuing the collaboration. Sometimes it is very intense collaboration, sometimes it is less. But few of the students, they are in touch and we are working together. So with this, thank you very much. And if you have any query,
thank you, Professor Alika, for the wonderful talk. And this was a lead of the technique and the applications of these people are shown. And I think the participants.
I can't hear you. Devendra, I can't hear you.
Oh.
I can't hear you.
Hello, can you hear me now?
Now I can hear you.
Okay, I am thankful to you for the wonderful talk, and I can see the same energy as I used to see in 90s. So with same enjoyment and same energy, you have given the talk, and this was need of the hour that pulse laser deposition techniques you have exposed to the participants, and now the participants who are the fresh researchers, they can decide their area of field, what to choose, and what can be done. And you have also covered some of the applications of thin films. So this was the enhanced knowledge given to them. So any participant would like to ask any question. In the chat box, there is no question. So I think there are no questions, and I thank you very much.